Okay, now let's talk about how to derive the equations for single slit diffraction. Okay, but before we go into derivation of equations for single slit, I need to go back to double slit. Yeah, I need to go back to double slit because there's one thing I want to show you. One thing I want to show you first. Okay, this young double slit. As you can see, you have learned about the small triangle before. Okay, this small triangle is referred to this triangle, this small triangle. Okay, which is sin theta equal to delta L over D. In fact, these equations is actually if we multiply the D, if you multiply the D to the top, okay, if we multiply the D to the top, what do we get? We will get d sine theta equal to delta L, isn't it? D sine theta equal to delta L. So this one, okay, you look here, yeah, d sine theta equal to delta L, this one. So if bright fringe, the delta L is m lambda, isn't it? M lambda. So m lambda substitute into this delta L over here. So we will get what equation? We will get the equations d sine theta equal to delta L. Delta L is m lambda for bright fringe because this is double slit is in phase sources. That's why delta L is using m lambda for bright fringe. Okay, now bright fringe delta L is m lambda. Just substitute into here. We will get the equation for bright fringe. For bright fringe is d sine theta equal to m lambda. Okay. M lambda. The same thing as the ym here. Ym here is m lambda d over d. This one d sine theta equal to m lambda also. So if d sine theta equal to m lambda, the ym also m lambda. You see that? M lambda, m lambda. Okay. If dark fringe, because this is double slit is two in phase sources. For dark fringe, the what I can say is the delta L, the path difference is m plus half lambda for dark fringe, m plus half lambda delta L. So d sine theta equal to delta L. This delta L substitute with m plus half lambda. We will get, what do we get? You tell me. We will get d sine theta equal to m plus half, sorry, yeah, hold on a second, yeah, we substitute the m plus half lambda into the delta L over here, so we will get this one, d sine theta equal to m plus half lambda. So for dark fringe, formula, double slit, dark fringe for double slit, actually it has two formula. One is the ym equal to m plus half lambda d over d. The second one is d sine theta equal to m plus half lambda. You see, if d sine theta has m plus half lambda, then the ym also m plus half lambda. If this one m plus half lambda, this one also m plus half lambda. Okay. Double slit, this is double slit formula. The bright fringe formula is d sine theta equal to m lambda, and then ym equal to m lambda d over d. For dark fringe, the double slit dark fringe is d sine theta equal to m plus half lambda, or ym equal to m plus half lambda d over d. So if you look at single slit, now you look at single slit, it also has almost the same formula. Do you see that? Just last time we use what? We use d sine theta equal to m lambda. Now we just change alphabet. From d become a, from m become n. From m become n. Last time we used d. D is the separation between the two slits. Now we use a. A is the size of the single slit. And then last time we used order m. Now we use order n. And then this one also almost the same. Last time we use, what last time our formula is, what is our last time formula? last time our formula is ym equal to m lambda d over d, isn't it? We use d. Last time we use d, now we use a. Last time we use m, now we use n. So it's the same. So as long as you see, if you have a sin theta equal to n lambda, if it is using n lambda, then the y also use n lambda. Just the same as before lah. Last time d sin theta equal to m lambda, y also is m lambda. Now it's n lambda, so y also n lambda. Okay? Alright. Now, now I want to go into here. Okay, I want to discuss about how to form the equations for single slit. Okay, how to form the equations for single slit. Now, this is very interesting parts. Yeah. Why do you learn about the formation of single slit diffraction? Why do you need to know that every point on the wavefront that falls on the slit? I always emphasize about this. That every point on the slit itself, every point of the wavefront on the single slit become the sources of many wave. Yeah, since they are not just 6 particles, actually there are many particles here, not just 6 particles. There are many particles. There are countless particles here in between the slits, and each of these points form their own wavelet. And this wavelet, they will, we can say, interference with each other to form this diffraction pattern. Okay, they will interact with each other, superpose with each other to form the interference pattern on the screen. Okay, so that's a very important concept. Okay, so let's look at this one. Yeah, so to begin, we need to divide into parts. Okay, we need to divide into parts to see how each point. Okay, as you can see here, there is a single slit here. You must know that along this slit. First of all, before we begin, you must identify what's the terms, what's the symbol involved. Okay, here we have symbol A. A is the size of the slit. That means how big is the slit, the size of the slit, the size of the slit, and yeah, we call it slit width, the size of the slit. Last time we use D for double slit. D is what? What is D? D is the separation. D is the separation of the two slit. Separation of the two slit. But this one single slit, this is the size of the single slit. Is the opening, the size of the opening. Okay, the slit width. The D, the symbol D for double slit, that one is separation between the two slit. This one is the size of the single slit. Yeah, the size of the single slit. How big is it? And D, big D is the same as double slit. D is the distance of the screen from the single slit. Distance between the single slit and the screen. That is the big D lah. Yeah, distance of the screen to the single slit. Now I want to explain. About what why do you need to consider about these many particles here. Yeah, we know that for the single slit there are not just 1 particle or 6 particles here. There are many particles here, and we cannot know how many particles in between. Each of these particles form their own wavelet, form their own secondary wavelet that interact with each other to form the interference pattern. I'm sure you in the secondary school you learn about diffraction grating before. You learn about this before. Yeah. If you have many sources of wave, this is how it happened. You see, each of these form their own wave, and we can say the crest overlap with the crest to form a constructive interference. The crest and the trough overlap, they cancel each other. Then you cannot see any wavefront. You can see dark fringe. The crest with the crest. Yeah, here you see the ray here. You can see this is the bright fringe it will form. This is like, you can imagine something like this. Yeah, each of the slit form their own wave, form their own wave, and all these overlap with each other. You see, overlap with each other. All the crest overlap with the crest, trough overlap with the trough, or crest overlap with the crest with crest, or trough with trough form the constructive interference. Crest with trough form the destructive interference, something like that. So the same thing happened as so the single slit is just like this. Single slit is just like this. Yeah, I can say that it's the same thing like for this one. For the single slit, there are many wave. Yeah, the wave. This is the first particle wave. The second particle wave also like that. Yeah, and then the third particle wave. And so on, and all the other partners. So it will constructive interference, and then destructive, and then form their fringes lah. Yeah, this is how it happens. Each point become the sources of wave. Understand? Okay, now let's consider. Yeah, so if we want to study how they overlap, because there are so many particles here, isn't it? We don't know how they overlap. We cannot know in a systematic method how to know they overlap with each other. Since there are millions of particles here, how they overlap with each other, we don't know. So we have a systematic way to investigate how the millions of particles here overlap with each other. That is by dividing into parts. By dividing into even parts and also dividing into odd parts. This might seem odd to you, but bear with me. Yeah, you go with me. You surely can understand. Okay, listen carefully. So what I can say is there are millions of particles overlap the wave with each other, and how to know they overlap with each other systematically? This is the way. Divide into parts, even and odd parts. Now, let's look at this one. Now I start with divide into even parts. Yeah. So divide into even parts. Okay, you see, so this is the slit. A is the slit width, the size of the slit. Okay. I need to make sure I'm recording. Yeah. This is the size of the slit, and now we divide into even parts. Divide into even parts. A divide by 2 become each parts become A over 2. Yeah, each parts become A over 2. And what I can say is in between in this slit there are millions of particles. There. I cannot draw all. I can only draw a few. You see that? There are millions of particles there, and each of them produce their own wave. And they interact with each other. Okay, they interact with each other. So so they produce their own wave. Yeah, they produce their own wave. Okay, they produce their own wave. Okay, and they interact with each other. So that's why this one actually I no need to draw so many things. Yeah, so I can say there are millions of particles here. They interact with each other. Yeah, how do each of these waves interact with each other? So that is by dividing into parts. Okay, there are many particles here. So now let us consider one by one. Yeah. Now A divide into 2. You have each parts become A over 2. Now look at here. I just take 3 points. To explain the beautiful process. All right, the beautiful process. Now look at here. Between A and C, I'm sure. Let's say want to form the fringe over here. The center is a central maximum. Now want to form fringe over here. We don't know what fringe it will form. We don't know is bright fringe or dark fringe over here. But let's look at here. Between A and C, which one travel further distance? A or C? Which one have to travel further distance? Of course, it's C. What I mean is we just take the particle at point A and particle at point C. That means we just consider these two waves. Yeah, the particle for point A will produce its own wave. And particle C will also produce its own wave. Understand or not? Produce its own wave. And then how do A and C overlap each other? And what kind? How they interference with each other, and they produce constructive or destructive interference? Okay. So now, first of all, look at the particle A and C. Okay. In fact, actually, particle A is the first particle. What I can say, first of all, particle A, you need to know, particle A is actually the first particle for the first strip. For the part, I can say for the part 1 lah. Yeah, part 1 means the first strip. Because I divide into two parts, isn't it? This is considered like part 1. This is considered like part 2. Even parts. I divide into two parts means I divide evenly. Yeah. I divide into two parts. I divide into even parts. Okay, two parts. Even parts, we have 2 parts. We have 4 parts here. Here we just have 2 parts. We also can divide into 4 parts. We also can divide into, what's the next one? 6 parts. Yeah, these are the even parts. You understand? Okay, later we'll know why we divide into these parts. Yeah. Okay, so A is the first particle for part 1. Okay, first particle that produce the wave. Now C is, what is C? C is the first particle. C is the first particle for part 2. We have 2 parts, isn't it? We already divide this slit into 2 parts. So A is the first particle for part 1. There are many particles following, and then C is the first particle for part 2. First particle, and B is the last particle for part 2 lah. B is the last particle for part 2. Now, you see, let's say this A and C, they destructive interference at certain distance up along the wave. This A and C, they overlap and they destructive interference and form a dark fringe over here. Let's say they form a dark fringe over here. Okay, what's the condition to form a dark fringe there for A and C? You see, this wave comes together. This is a one single wave coming, isn't it? We can say actually A and C, they are in phase source. A and C, actually they are in phase. Well, I can say they are in phase source. Why they are in phase source? Why A and C are in phase source? Because they receive the same wave. They receive the same wave, isn't it? The wave coming and reach A and C at the same time. So they receive the same wave. They receive the same wave. So we can say A and C, they are in phase source. So how to produce a dark fringe there? How to produce a dark fringe there? For in phase source, this is very important. For in phase source, how to produce a dark fringe there? You see, just now I mentioned A travel a shorter distance, C travel a longer distance, isn't it? C travel a longer distance. And how to produce a dark fringe? The path difference. Do you remember what we learned about the path difference? About these two slits? About this S1 and S2? If these two S1 and S2, let's say if let's say this S1 and S2, they are both in phase sources. They are both in phase sources. So we know that S1 travel a shorter distance, S2 travel a longer distance. S2 travel this amount of extra distance, yeah, delta L. If delta for in phase source, remember, for in phase source, the delta L must be equal to, let's say the delta L equal to, let's go back to this one, in phase and anti-phase. If in phase source, to produce the bright fringe, now we are talking about in phase source only. So in phase source, to produce a bright fringe, the delta L must be multiples of lambda. Multiples of lambda. To produce a dark fringe, the delta L must be m plus half lambda. In phase source, to produce bright fringe, the delta L must be m lambda. To produce dark fringe, the delta L must be m plus half lambda. Isn't it? Okay. So let's go back to this one, just now this one. Okay, so let's say S1 and S2, they are in phase source. So let's say now I want to produce a dark fringe. Now I want to produce a dark fringe here. So this, what's the path difference delta L should be? For in phase source, to produce a dark fringe here, this delta L need to be m plus half lambda, isn't it? Need to be m plus half lambda. I say already, kan? In phase source, to produce dark fringe, the delta L must be m plus half lambda. Must be m plus half lambda. M plus half lambda, then only can produce dark fringe. So it can be let's say it can be half lambda, it can be 1 plus half lambda, can be 2 plus half lambda. As long as has that half lambda, then can produce the dark fringe already, isn't it? If this delta L is 1 lambda, 2 lambda, 3 lambda, m lambda, it will produce bright fringe. If it is the delta L is equal to 1 lambda, 2 lambda, in terms of m lambda, this one will produce bright fringe, isn't it? For in phase source. For in phase source. Now, okay, now these two wave, now I'm talking about in phase source. Now these two wave, I want to produce dark fringe. Okay, I want to produce a dark fringe over here. So this delta L need to be m plus half lambda. Okay, now you get it. If in phase source, delta L must be m plus half lambda to produce dark fringe. Okay, now let's look at this single slit. Single slit. Now, this particle A and C, or we can say wave A and wave C. Two wave A and wave C. Two wave only. I'm only talking about these two wave because this will affect the rest. These two wave are the most important one. Wave A and wave C. Wave A and wave C. And my condition is I want to produce a dark fringe here. I want to produce a dark fringe here. Wave A and wave C, they are in phase source because they receive the same wave. They receive the same wave and they receive it at the same time. This wave A and wave C, they are in phase source. Don't talk about anti-phase because we are not talking about anti-phase. Anti-phase, then the whole thing will become different already. Then anti-phase, the delta L become different already. Become opposite already for bright fringe and dark fringe. Okay, I'm not talking about anti-phase. I'm talking about in-phase source. Okay, so let's look at this one. Wave A and wave C, they are both in phase source. Okay, wave A and wave C. Now my condition is I want to produce a dark fringe here. I want to produce a dark fringe here. I know that wave C travel a longer distance compared to wave A, isn't it? Wave C travel a longer distance. By how much? By this amount. This is the delta L. Yeah, I just want to draw it out. I just want to draw it. This is the extra distance by wave C. Okay, this extra. I can say this. The part I draw out. This is the delta L. Okay, delta L. So I want to produce a dark fringe here. This delta L for in phase source. In phase source, to produce dark fringe, delta L need to be m plus half lambda, isn't it? To produce a dark fringe or in phase source, this delta L need to be m plus half lambda. Okay, now I just put the m equal to 0. That means I just put it as what I can say is start with half lambda. I start with half lambda. I start with half lambda. So if this, let's say, if this delta L is half lambda, the wave A and wave C, will they produce the dark fringe there? Of course, they will produce a dark fringe because the path difference is half lambda. because we can say this we can say this is the first fringe from the central maximum. This is the first fringe from the central maximum, and the nearest of these fringes to the central maximum is when this delta L is half lambda. Okay, is half lambda. If we put why I don't put 1 plus half lambda? Why I don't put 1 plus half lambda also can produce that fringe? Why I don't put 1 plus half lambda? Because if delta L equal to 1 plus half lambda, means it's already further up the screen. That is the next fringe already. I don't want to consider about the next fringe. I'm now considering the beginning, the first fringe from the central maximum. Understand or not? That's why I don't take 1 plus half lambda, because that delta L is longer already. That delta L is longer. That longer delta L is for the next fringe already, further up the screen. Understand? So I don't take that one. I take the smallest delta L. Because that is the nearest one to the central maximum. That's the nearest one to the central maximum. Okay? Now you clear? Okay. Now, if this delta L is half lambda between wave A and wave C, and wave A and wave C, they are in phase source. When wave A and wave C, they are both in phase source, and their delta L is half lambda, means they definitely form dark fringe over here, isn't it? Okay, good. Now, what I can say is here. Look at here. The first particle here. So now it produced a dark fringe here. So what I can say, wave A, the first particle for part 1, and the first particle for part 2, or we can say wave A and wave C, they cancel each other. Yeah, you see here, I draw it out. Yeah, the wave A, this I use what color? The wave A, this the first wave, and the first wave here cancel each other already. The first particle for part 1 and first particle for part 2, they cancel each other. Because their delta L is half lambda. They cancel each other because the delta L is half lambda. So they cancel each other, produce dark fringe. Now, what's the following one? I move down one particle. Here. Now I talk about second particle of part 1. And then the second particle for part 2 also. I move down one particle. And also I move down one particle. This one, the part 1, I move down one particle. Part 2 also I move down one particle. Okay? So what about the delta L? What about the delta L between the second particle and also the second particle? What is the delta L between the second particle of part 1 and what between the, what I can say? Okay, the delta L for first particle in part 1 and first particle for part 2 is half lambda. So the delta L for the second particle and the second particle here should be the same, half lambda also, isn't it? So that's why the second particle wave, you know, this second particle also produce their own wave. And this second particle also produce their own wave. Since the first particle and first particle delta L is half lambda, so the second particle and the second particle, the delta L also half lambda. Because just the one next to it, yeah? Just the one next to the first particle. The first particle and the first particle here, delta L is half lambda. So the second particle and the second particle here, the delta L should be half lambda also. So they also destructive interference to form dark fringe. They cancel these two, the second particle wave and the second particle wave for part 1 and part 2, they also cancel each other to produce dark fringe. They cancel each other. So how about the third particle? How about the third particle in part 1? How about the third particle in part 1? And how about the third particle in part 2? Also, delta L half lambda. So cancel each other. dark fringe. How about the fourth particle and the fourth particle? These two, the fourth particle and this fourth particle, the delta L also half lambda, also cancel each other, produce dark fringe. So what I can say, out of this, in a conclusion, what's the conclusion? Let's hear about the conclusion. Okay, let me just remove all these. So what I can say is all the particle here, all the particles in the first strip is being cancelled off by all the particle by the second strip. The first particle cancel the first particle light, the second particle light cancel the second particle light, the third particle light cancel the third particle light. Because the path difference delta L is the same, half lambda. Understand? So the first strip light being cancelled by the second strip light. So in the end, it produces a dark fringe over here. I produce a dark fringe over here. Understand or not? That's how it works. That's how it works. That's how we investigate the interaction of millions of particles in between the slit systematically by dividing into parts. Understand or not? So as long as you have even parts, all of them will cancel each other totally to produce a dark fringe. For all of these will produce dark fringe. You see. Never mind, we will see later on. Okay, I think that's enough for the first part of videos. Yeah, let me continue with the next video. Okay, thank you very much.